Started. Welcome to the sponsorship session. And today we invited a speaker from Google DeepMind. And I will let the speaker introduce himself. Hello, everyone. My name is Jay. I'm from Google DeepMind. I'm a research scientist. And today we're going to talk about path towards generalization. Where are we, and what are we missing today? In particular, I want to share my perspective as a research scientist who lives and works in Silicon Valley, because a lot of things are happening there. So robotics is making rapid progress. Right? These are just 4 videos you probably have seen, very impressive videos that was released in the last 2 weeks. So you might be wondering why suddenly we make so much progress in just a year or 2. I think there are 3 main reasons. First of all, we get access to these very cheap and reliable hardware. Second, there is this neighboring field, LLM and VLM. They are making very rapid progress. They capture the world knowledge and can generalize really well. And we start to believe that this might be the perfect candidate to build the robot brain. And the third, because this person, no matter whether you like it or not, when Elon Musk says something about technology, the VC listened. He said that, I think by 2040, there will probably be more humanoid robots than there are people. This explains why suddenly, in Silicon Valley, all these startups start to boom with very high valuations. Even myself and also a lot of my colleagues get calls from VC from time to time. You might be interested in what kind of conversation look like, because VC ask billion-dollar questions, right? So I want to summarize these conversations. So usually, they ask you 3 types of questions. First, what is Google working on? Do we miss something that you guys know, but we don't know, so we are going to miss a huge opportunity for investment? Second, I have heard this pitch. Do you think it makes sense? Is the technology ready? Is now a good timing to do it? And all these conversations usually ends with, are you going to do your startup? When are you going to do it? So I hope that today I prepared a presentation that can shed some light to the answers of these questions. Hopefully, it can help you to steer your own research direction, or maybe serve as some career advice. Let's start with the first one, what Google working on? So we usually think from the first principle and want to understand what is the most critical capability for robotics. So in the future, robots is going to enter our lives. They're going to be everywhere, in factories, at home, in the wild, and interact with people. So it's very unlikely that we are going to engineer everything or collect all the data that cover all these special cases. These robots are going to operate in out-of-distribution scenarios. So they should still work. Generalization is probably the most critical feature for robotics. Unfortunately, it is also one of the biggest bottlenecks today. So on the left, I want to show you a video. It's very popular on the internet. This is a failure compilations of Mobile Aloha, shared by the authors. I love Mobile Aloha, and they're impressive. But when the robots encounter unfamiliar scenarios, they fail catastrophically. Okay. There is another example, RT2. Right? RT2 claimed to made a lot of progress in generalization because it leveraged the vision language models. However, you can see that it failed to pick up these apples. Simple task. Because the size of the apples is much smaller than the size of apples during training time. Here is another anecdote. So every Christmas, before the Christmas, we are going to do robotics show and tell to the VPs of Google DeepMind. People like Jeff Dean or Demis are going to come to check the robotics demos. So usually, we are going to pray, tomorrow is going to be a sunny day. Please don't rain. Because if it rains, the lighting condition is going to shift drastically in the labs. That will be very out of distribution from the data collection time. So generalization is not solved. How can we solve it? Many of us believe in robot foundation models. which is a natural extension of the vision language models to include actions. We hope that these models can capture the world knowledge and generalization from vision language models, but also output actions to change the real world. Robot foundation models is not a stranger for this community, for this audience, and Google has been working on this for quite a few years now. We start from RT1, then we build RT2 and RTX. Many people ask me, what's next? We are working on it, and we have very exciting progress. But today is a bit too early to disclose it, but I still want to share some of the learning we have along the way and a few key ingredients to build this next big thing in robot foundation models today. So when we think about robot foundation models, in many people's mind, it looks like this. So we have the model, those are pre-trained, and we got the checkpoints, right? PaLiGemma, Llama 3, Gemini, GPT, we get the checkpoints. What's missing is only data. So people go outside, collect a lot of data in the real world, then put them together. So this data collection is like an afterthought. And they duct tape them together. And this duct tape is called imitation learning or fine-tuning. But we think slightly differently. We think that the model and data is like a continuous spectrum, and you need to co-develop them together. So today we're going to talk about the 3 research areas along this continuous spectrum. How can we mine existing knowledge from vision language models? How we can improve some of the missing capabilities, such as the embodied capability of future generation of vision language models. And very importantly, how to find the right interface between vision language model and robot actions. And I'm going to sample very quickly 4 recent papers along this spectrum. Let's start with Pivot. Iterative visual prompting elicits actionable knowledge for vision language models. So visual prompting is a way that you can present vision language model an image. Then you do some markings, scribbles, annotations on the image, and then ask questions about these markings and image. So visual prompting is a very strong capability of vision language models because there's a lot of training data in the vision language models that are drawn from the draw annotations on the image. They are very, very large, abundant on the internet. And here is a quick example of how Pivot works. So basically, when you say, I'm thirsty, what should I get? Then you start to draw these arrows and circles, then query vision language model. And vision language model is going to give you good suggestions. It always points towards this drink. Similarly, where to throw this away, and vision language model is going to recognize you are taking a Coke can, and it's recyclable, so it should be put into the recycle bins. So here's a little bit more detail how it works. For robotics applications, we first start to sample the action space. For the navigation problem, it's wheel speed. For the manipulation problem, it can be the position of the end effectors. The second step, you project them into the image or the observation space. And then you draw these arrows and the circles to annotate the actions. Next, you query the vision language model. If I want to accomplish this task, which arrow should I follow? And vision language model is going to give you a set of suggestions. But we don't directly apply the best suggestion on the robot, because vision language models are not perfect. They often make mistakes. So we want to get more votes and drive some consensus along the way. Basically, we pick the top suggestions and fit the distribution to it, and then we iterate and execute. This whole process looks like a method called CEM. I don't know whether you guys know it, cross-entropy method. Basically, you have the iterative method to optimize the objective function. So far, I have not made any assumptions about the robots, its embodiment, the task, or anything like that. It's a very general interface that enables cross-embodiment and multiple task executions. For example, you can have a navigation task, ask the robot to find a table with tissue paper on it, or go to the wooden bench without hitting a trash can. or guide me to a place where I can sit and write. So the vision language model really understands the language instructions, understands semantics of the scene, and then can gradually guide you to the proper place. Also, it works for manipulation tasks. And here you can see that we ask the language model or the robot to put the fruit into the corresponding bowls. So in summary, Pivot leverages the world knowledge of vision language models and makes it actionable for robotics. But here, I'm not saying that this is the best way to put vision language model and action together. This is actually the first time we tried vision language model and tried to explore its boundary and limitations when we want to apply it to robotics. So there's a lot of limitations, and the success rate is not that high. So one limitation is that we find the vision language model has relatively poor spatial understanding and reasoning. And the second one is visual prompting does not help with fine-grained control that requires physical interactions. So now we know the limitation. The key is we want to improve these. The second paper, Spatial VRM, is going to target at spatial reasoning and understanding. We humans use spatial reasoning a lot to make decisions, and hopefully robots are the same. However, the latest vision language model isn't great in spatial reasoning. For example, if you present an image to the vision language model, you say, I'm a cleaning robot, I'm 1 meter wide, I want to go through this path between the sofa and the chair and table. Can I go through it? So here is ChatGPT 4V's answer. It gives you the wrong answer. It estimates the gap size too narrow, so it says, no, you cannot go through it. And we believe that this lacking of spatial understanding is because of lacking of this spatial understanding data set when we train these vision language models. A lot of the training data sets are the image and the paired caption of the image. Basically, these are the description of the image instead of deep understanding or spatial reasoning. To solve this, we start to do some data engineering. We want to create a large data set about spatial reasoning. So we mine or we crawl a lot of image from the internet. Then we filter out those images that you cannot ask reasonable spatial understanding questions, such as a cartoon. Then we leverage all kinds of vision expert models to lift different kinds of information, such as caption, depth, segmentation, and so on. Then based on these information, we are going to generate a huge set of Q&A pairs about spatial reasoning. And there are two types of Q&A pairs. One is qualitative, where you ask a question, you expect a binary answer. For example, whether this person is in front of the chair. Or you can ask quantitative questions, such as measure the distance or estimate distance between these two objects. So by training the vision language models with these additional data, we find that spatial VRM outperform the state-of-art vision language models in these spatial reasoning tasks, no matter it's qualitative or quantitative. Let's go back to the initial motivating example. If you ask a spatial VM, should the robot go through this path, it will use chain of thoughts reasoning and give you the right answer. It estimates that the gap is about 1.56 meters wide, and the robot should be able to go through it because the robot is smaller, or the width is smaller than the gap. You might be wondering that this is one way to improve vision language models. How does it connect back to robotics? As I mentioned at the beginning, spatial reasoning is critical for robotics. So let's make sure that we can get things right for robotics applications. The first thing we ask is to see whether, if you give the spatial VRM these robotics images, whether it can successfully or precisely predict what's the distance between objects. So we ask what's the distance between the end effector and the cocan throughout this continuous sequence of the videos. And the estimation is on the right in the green curve. And it correlates really well with the ground truth where these yellow dots is. But how can we use it? Remember the pivot? You can always draw these dots and ask the VRM to pick the right dots. Now you have this ability to estimate distance, and the pivot is going to give you better results. Now we have a model that is equipped with great spatial reasoning and spatial understanding. What about physical interactions? In DemoStart, we introduced an end-to-end system that can use reinforcement learning to generate a lot of data in large scale in simulations, and we made it work in real world. And this data collection is perfect for building the robot foundation models. So in particular, we choose to use this platform called DexHand. It has 3 fingers, 12 degrees of freedom. It needs to learn very dexterous tasks like this one, where it pick up a block and insert it onto the socket. And obviously, it's a very challenging dexterous task that requires a lot of precise physical interactions. So when people think about how to enhance foundation model with physical understanding, people collect data. They build these large farms of robots and hire a lot of people to teleop it. I think there is a better or more scalable alternative. That is to use simulation. Many teams and groups have been working on it, but there are 2 key challenges. One is, how can you get your initial policy that can give you consistently success episodes? Because at the end of the day, we are using imitation learning. We want successful episodes. So the second question is sim-to-real gap. And we are going to explain some of these here. The high-level overview of the method is that we start with very few suboptimal demonstrations. Then we use reinforcement learning to learn a policy to extrapolate these demonstrations to a much wider space and collect tons of data as a scalable way to do data collection. Then we collect all these data and distill them into a model. This model can be a smaller model. It can be a robot foundation model. And then we deploy on the real world, and it works. So very quickly, I think the key challenge is how to use RL to get a successful policy for such a dexterous task. And we use curriculum learning. The idea is very simple, right? You start from the goal, and then you change your initial condition gradually from the goal to the initial condition. In this way, you construct a curriculum from easy task to harder task. But the question is, how can you sample these initial conditions? So we introduced a method called zero-variance filtering. So with a set of candidate initial states, you are going to roll out the current policy and see what's the variance of the rewards. If the variance is 0, for example, it's all fail, or it's all success, it means that the task here is easy, too easy, or too hard. And it's not very informative if you start from the current initial condition. Rather, you want to pick initial conditions that has a mix of failures and success. And this is the most informative initial conditions. So with that curriculum, it's all automatic. You can see some of the simulation results where the robot can learn successfully these very, very dexterous tasks with only a handful of demonstrations. And we collect all these simulation trajectories in a data set, and then we train a model and deploy it in the real world, and we can successfully overcome the sim-to-real gap. So a quick takeaway of this project is that simulation is a scalable way to collect data for robot foundation models. We find that RL with auto-curriculum in simulation can quickly 100x or even more than human teleoperation. One thing that I don't have time to cover is sim-to-real gap. You can read the paper for details, but we find that domain randomization and realistic rendering are the key to reduce the sim-to-real gap for this project. Now we have measured the limitation of the VLMs, and we have a few ways to improve the VLMs. You might be wondering, where is the actions? So if I go to the keynote talk on Monday, Thomas said that one of the key ingredients to solve generalization is modularity. And the key of modularity is to determine what are the signals that flows on the wires between 2 modules. I cannot agree more. So what is the right interface between vision language models and robot actions? The ideal interface should stay very close to the training data of vision language models, so it can extract and leverage the knowledge in vision language models. At the same time, it serves as a condition of the low-level policies. So we hope that the policy will be easy to train with this conditioning, and at the same time, it's generalizable. The team at Google have tried many different interfaces in the past few years. We have tried language, trajectory, reward, code, video, and many, many others. And today, I want to highlight one that's very interesting and exciting, which is trajectory. And here's an example. So who will provide these trajectories? So these are trajectories on the image space. Human can do it. So we can draw trajectories and guide the robot to solve the task. At the same time, there's this foundation model that is good to understanding these trajectories because visual prompting, because of the data, the training data often involve these trajectories. They can also provide reasonable trajectories. And once these trajectory is provided, we need a policy that can follow the trajectory to accomplish the task. So here is a high-level idea of RT trajectory. We already collect all these robot data. In hindsight, we can extract these trajectories in the image space. Then we train a RT1-like architecture that takes in the observations and trajectories and output the actions. As I mentioned, during test time, human can draw these trajectory to guide the robot, to teach the robot, or we can actually extract trajectory from human videos because it's very easy to identify a hand, then you can draw the trajectory of the hand motion. It's like learning from human videos. And finally, and more importantly, we want that the foundation model can also draw these trajectories. So we have done comprehensive evaluation on generalization for different type of task. And we find that RT trajectory performed the best compared to a few baselines, including RT1 and RT2. Also, we find that these foundation models, VLMs, LLMs, they are good at, or even image generation models, they are pretty good at generating these trajectories given the language input. And you can see that these are for different tasks. They can generate these screen space trajectories, and it can also encode like a time and height using the color of the trajectory. And then RT trajectory can follow these trajectories to accomplish the task. The takeaway of this project is that the choice of interface between vision language model and action policies greatly impact the generalization ability. So RT trajectory demonstrates one of the best generalization we have seen so far. And more importantly, foundation models can output reasonable trajectories thanks to the large amount of training data with image and annotations. But there's still a lot of room to improve for language models or vision language models to understand and predict these trajectories. But once we know and identify these limitations, we can engineer a large data set to improve it. In summary, generalization is one of the most critical features for robotics, but it remains an unsolved problem. There's a lot of foundational research need to go in to solve this problem. And we believe that robot foundation model is a promising direction towards generalizable robot control. And we have invested a lot of time in these three areas: mining the existing generalization capability that are already embedded in vision language models, identify the bottleneck and improve vision language models' missing features for robotics by collecting relevant data in a scalable way, and finally, find the right interface to connect the vision language model's world knowledge with the multi-level action. I hope that my talk has answered all these three questions. Just to make things more explicit, let us review them together. So what is Google working on? As I mentioned that we are working on the next big thing after RTX. Today is a bit too early to disclose this, but stay tuned, it's coming soon. But today we have talked about 4 main ingredients to make this thing happen. Is now a good time for robotic startups? I think different people will have different opinions. For example, at Gartner Hypercycle, so this is a survey by Gartner, they think robotics is here, it's going downwards into the trough of disillusionment. I slightly disagree. I think robotics is probably here. There's still a lot of hype, so it's along the peak. But I think everyone agrees that it still takes a lot of time to solve these foundational problems to really solve robotics. It's still probably 5, 10 years even longer, before humanoids is going to enter our homes and doing all the daily chores for us. So is it a good time for startups? Maybe. But I want to present another alternative, which, in my personal, very biased opinion, a better alternative. Google DeepMind is one of the best places to advance robot foundation models. Why is that? Just think about what you need to build a foundation model. You need a great model to start with. You need a lot of data and a lot of compute. So at Google DeepMind, we have all kinds of some of the best foundation models. We have many different types of robots and many people to collect data in the real world. We have the state-of-the-art simulation to even scale up data collection. We have a lot of TPUs, GPUs, and CPUs. More importantly, we have a very dedicated team of passionate and talented people. We are hiring, and welcome to join us. Thank you. Any questions?
Hey, great talk. You didn't answer the third question. When are you starting your startup?
So I think when you guys are going to start your startup, yeah. I think I answered the third question by showing you that, in my opinion, Google DeepMind is a better alternative than doing my own startup at this time.
Hey, thanks for the talk. Speaking about generalization, you mentioned this distinction between the kind of high-level planning generalization that language models and so on give you, and then there are the fine-grained motor policies.
Yeah.
But those also struggle to generalize, right? So when the apple is a little bit smaller. When the apple is a little bit smaller, it doesn't work anymore, and so on. Can you say something about your attempts to improve generalization on the low-level motor control side?
Yeah, so that is exactly the last project that I want to emphasize is by using different kind of conditioning, you are going to get very different kind of generalization in the low level. And we have explored many ideas. I think so far the RT trajectory, where the conditioning is the trajectory, give us the best generalization. So you want a great generalization on the high-level plan. You want great generalization on the low level. Then finding the right interface is the key.
Thanks.
In the back. Thanks, Jay. Nice talk. And I was wondering, when you're always talking about these large models, and we always say that they are kinematic trajectories. And when we talk about the real-world interactions, we also talk about force. And this force-level interactions is also very important. And we see Meta's progress on tactile senses. What's Google's take on this?
Yeah. So we also believe that the low-level dexterity, the low-level interaction is super important. So the third project I mentioned is how you can augment the vision language model to really understand these detailed interactions. So that's one thing. The vision language model, even at the high level, should understand it, so it outputs the right conditioning for the low level. At the same time, the low level, currently many people using diffusion models, using other models, is to improve generalization, is to improve dexterity, and for the better interactions. So you need to do it both on the high level and the low level. Any other questions?
One more in the front.
But is there a good tactile simulation for your reinforcement learning event when you want to improve your models in simulation?
Yeah, so in simulation, it should be easy to get the contact information. It might not exactly match the tactile sensor will give you, but by default, in simulation, you can get whatever you want, right? So you naturally already have the tactile sensor or tactile information in simulation. And we have not tried extensively to include the tactile signal into reinforcement learning. So that's definitely a great next step. So if there's no other questions, I can end here. I will stay at the Google DeepMind booth in the next 1 hour on ground zero. So if you have more questions, welcome to talk to me. Thank you.
Hello. Hi, everyone. I'm Andrea Baichi. I'm an assistant professor at CMU, and together with
I'm Xiaorong Wang from UCSD.
we're going to be chairing the next oral session. So if you are presenting in the session, please come down to the front of the stage here and line up in order of your presentation. We will start by having Keiyu Chen come up to the stage. Do you have your adapter? Yeah. And then I'll introduce you in a second.
This HDMI, do you have it? Okay. Oh, he needs a adapter.
You need a separate. Do you have audio? No. Okay. Looks like it's ready, and then we'll put it up.
All right. So we are ready to kick off the next session. Keiyu Chen will be presenting Freya. Take it away.
Hello, good morning. My name is Keiyu Chen, a second-year PhD student from Tsinghua University. It's an honor for me to present my recent work, Freya's, focusing on safety-critical scenarios generations for the autonomous driving. So what are the safety-critical scenarios? They involve the situations where the autonomous vehicle must quickly respond to unpredictable factors, like jaywalkers, unusual objects, or glare. These moments are crucial for evaluating whether the autonomous vehicle can handle the corner cases. However, safety-critical scenarios are rare in the real world, and manually design these scenarios is just impractical. Therefore, automatic generations is crucial for advancing autonomous driving systems, especially for those learning-based methods which requires diverse training data. Existing research view this as an attacking problem and use collision-driven methods like optimizations, reinforcement learnings, and deep generative models to generate safety-critical scenarios. But is the collision-driven adversarial attack really the right way to go? We believe this focus might be misleading. The first reason is that in the real world, driving behavior is often goal-driven or route-driven. Therefore, in some situations, vehicles sharing the same driving destinations and showing aggressive behavior, and that will lead to safety-critical scenarios. So collision is the consequence, not the objective. The second reason is that collision-driven attacks often create unreasonable and AV-feasible scenarios. This also means that in some scenarios, the AV is doomed to crash, and there is no policies can ensure AV's persistent safeties. This kind of data can be just poisonous for AV trainings. Therefore, our methods aim to create adversarials while AV-feasible safety-critical scenarios. Specifically, we use the feasibilities of the autonomous vehicles as an upper bound of the adversariality of the scenarios, and trying to maximize that while keeping the feasibilities of the autonomous vehicles. To create reasonable adversarial scenarios, we first select some background vehicles that might have conflict with the autonomous vehicle as the critical ones. Then we just control their behaviors and use a goal-based reward settings that encourage the CBV to reach some reference point on the AV's global path, and thereby introducing interactions between vehicles and increasing the adversarialities. Then, to create AV-feasible scenarios, we apply the concept of largest feasible regions following RCRL and FASOs, which utilize the HJ reachability framework to describe the worst-case constraint in safe reinforcement learning. And this framework focuses on persistent safety instead of the current safeties. Since determining the true largest feasible regions required Monte Carlo estimations, and that is impractical in the dynamic driving environment, so we adopt the methods proposed in FESOS, which utilize the offline reinforcement learnings to approximate the largest feasible regions. Specifically, we first collect data on the different AV methods in the color simulators and use it to train the feasible value network through offline reinforcement learnings. The visualizations of largest feasible regions also confirm the reliabilities of this well-trained network across different scenarios. With the approximate largest feasible regions, we further modify the RL framework for the CBV and adopt a feasibility-dependent training objective. Intuitively, when CBV's behaviors guarantee AV's feasibilities, we still use the adversarial's objective. But while AV is infeasible, we try to minimize the severities of the infeasibilities, which ultimately makes CBV's policies adversarials yet AV feasible. Building on that, we just replace the original's advantage functions in the famous PPO methods with our feasibility-dependent versions to complete the overall FRIA framework. This training framework comprising two parts. The first one is the offline learning, the largest feasible regions, and the second, the online part, is to guide the policy trainings of the CBV. In our experiment, we evaluate FRIA against several baselines to demonstrate its abilities to generate adversarials while AV feasible scenarios, and its effectiveness in AV system testings and training. As for the adversariality, since we care much more about near miss instead of collisions, so we use the matrix like time to collisions and post-encroachment time to quantify near miss event. The result indicate that FRIA generate many near miss events at the rate comparable to purely adversarial methods. And the BV map also shows the existence of the near miss event. Since we care about AV feasible scenarios, so purely adversarial is not enough, so we introduced the feasibility matrix like infeasible ratios, infeasible distance, etc. The results show that FRIA outperform others by achieving the lowest AV feasibility violations. To actually use these scenarios, we conduct AV testings and training experiment under the safe bench framework. The results show FRIA generalized well in AV testings due to its AV-independent training objective. Additionally, AV trained with FRIA demonstrate improved performance, benefiting from the feasible near-miss data provided by FRIA. Here we just present some representative scenarios generated by FRIA. It is clear that FRIA generate many near-miss events without collisions, such as sudden overtakings, intersection U-turns, etc., which is impossible for the collision-driven method. At the same time, we acknowledge that our method is still in the early stage and have some limitations. For example, the naturalness of the CBV behaviors need further enhancement, and the traffic common sense should be further integrated. This is not surprising since the overall framework of FRIA is just purely a safe reinforcement learning framework. So future directions including integrating much more real-world data to increase the naturalness and using the large language model to enhance traffic regulations. So for more information, please just scan the QR code shown here. Thanks for your listening.
Fantastic, thank you so much. Questions? Maybe I'll ask one question while we let the audience think. Yeah, thank you for the great talk. I'm curious, a lot of near-miss scenarios between multiple agents and driving can come not just from open scenes, but because of other objects in the scenes. There's maybe debris. There's like a plastic bag floating around on the highway, and it causes people to sometimes swerve, sometimes not. How do you think about including these other types of aspects of the environment that influence agents into your scenario generation pipeline?
Okay, you mean some more traffic scenarios, just like the highway or such kind of scenario, not just the intersection, right?
And not just kind of empty road.
Empty road, yes.
Like there's
in our simulator, since the color is the open source simulators, and it can add the object that you want, just like vehicles, pedestrians, cyclists, such kind of things. And you can just also put some object on this. But to be honest, in our framework, we put a lot of pedestrians and cyclists and vehicles. This is not usual in the previous work. And in the future, I think, since the safety critical scenarios is just not the behaviors of the vehicle, it should include some much more diverse objects, so it should be a very good directions. And we will consider about adding, for example, some unseen object in the vision systems, not just in the traffic simulations. Okay, thanks.
Any other questions from the audience? Well, then let's thank the speaker one more time. And next up.
All right. The next talk will be from John Subasides on one model to drift them all.
Right. Hello, everybody. Today I'll be presenting our work, One Model to Drift Them All, a conditional diffusion model for driving at the limits. The team includes my colleagues Frank Chimu, Thomas Lev, Nan Ding, Michael Thompson, Makoto Sumanaka, Marcus Grief, and me, John Subasides. So our team is studying driving at the limits of handling, that is, operating in regimes where the tire forces generated through friction with the road are saturated, and the vehicle may be literally sliding across the road. These regimes occur, for example, in racing and drifting, but also in other scenarios, such as driving in snow and ice, or when you're trying to avoid a sudden obstacle. Designing controllers that can operate safely in these regimes could potentially allow us to make cars much safer. However, today, controlling a car in such scenarios is challenging and is typically only done by expert drivers. Existing optimal control techniques for driving at the limits are sensitive to model mismatch, especially the misestimation of friction between the tires and the road. Data-driven modeling techniques allow you to more accurately characterize the vehicle's behavior, but existing techniques make unrealistic modeling assumptions and don't necessarily characterize the entire range of possible vehicle responses. In contrast, parameters of a physically meaningful vehicle model are a very compact representation of these responses, but estimating these in a global way is challenging to do in real time. Despite the fact that we can't know these parameters exactly, we would like to have a model capable of capturing the full range of possible vehicle responses while being computationally cheap enough to use for real-time control. Diffusion models are an appealing option since they have been shown to accurately characterize multimodal distributions over future trajectories, as well as sequences of inputs. However, inference with these models is computationally expensive, and they do not naturally accommodate physical knowledge of the system, meaning that generalization outside your training data set is not guaranteed. The key insight in our work is to use the diffusion model not to represent a conditional distribution over future trajectories directly, but over vehicle model parameters. We can then use a model that's appropriate for the task at hand, such as a neural stochastic differential equation that includes our knowledge of basic vehicle dynamics. So how can we train a diffusion model that has the desired properties? First, we use nonlinear optimization to label an existing library of trajectories with a set of parameters that best describes the vehicle's local behavior along that trajectory snippet. Then, as is standard for denoising diffusion models, we corrupt these vehicle parameter estimates, theta, with Gaussian noise and train a model to denoise these corrupted samples conditioned on recent vehicle behavior. Once the diffusion model has been partially trained, its conditioned outputs can be used as better initial guesses for the nonlinear optimization routine. When it comes time to deploy these models online, we can draw samples of the vehicle model parameters from the diffusion model conditioned on the last several seconds of the vehicle's trajectory. The best set of candidate parameters is then selected for use in model predictive control. Critically, the frequency of diffusion model inference and real-time control are decoupled, allowing us to run the model predictive controller as fast as is necessary, while the diffusion model can run much more slowly. effectively giving us the best of both worlds. We trained this framework on a collection of trajectories from 2 of our test vehicles, which have very little in common besides the fact that they are both rear-wheel drive. We observed that the diffusion model augmented approach was able to match the performance of an MPC that was trained with a model that was specific to a tire vehicle surface condition. In essence, the ability to generalize costs you very little in task-specific performance. The only differences in the vehicle control code across all of these autonomous tests is the desired trajectory and the MPC cost function weights, which are fixed for each car. To our knowledge, we are the first to demonstrate vehicle-agnostic control capability when driving at the limits. The controller performs well on our Supra that has been heavily modified for drifting. At the other end of the spectrum, here is a nearly stock LC500 drifting a course that was not seen in the diffusion model's training data. Later, we were fortunate enough to be able to test the approach in wet conditions, where tire grip is at least 20% than it is in dry conditions. Retraining the diffusion model from scratch with 7 wet weather trajectories added to the 84 used in the dry data set allowed the model to adapt to conditions where the dynamics are significantly different. All right, looking ahead to some potential future extensions of our work. First, we're interested in using multiple samples from the diffusion model inside the stochastic MPC problem to more intelligently reason about possible vehicle responses and operate more robustly in these regimes. Second, we are interested in exploring the applicability of this method in other robotics contexts beyond autonomous driving and autonomous drifting and racing. Finally, we are exploring conditioning the vehicle parameter estimates on sensor readings other than vehicle trajectory history. This should allow the model to better anticipate environmental impacts, such as hitting a sudden patch of ice. All right, today I'd like to leave you with 3 key takeaways from my talk. The first is that this hierarchical approach combines the expressiveness of a diffusion model with the high rate replanning and reliability of model predictive control. Secondly, we can easily leverage physical knowledge or other inductive priors in the lower level control-oriented model. While the ability of diffusion models to represent complex multimodal distributions allows us to draw on prior experience to quickly adapt in real time without having to explicitly perform system identification. All right, with that, I'd love to take any questions.
All right, thank you for the cool talk and very cool results. Are there any questions from the audience? All right.
Oh, hi. Thank you for the great talk. And I have a question about how this generalized to, for example, the sudden takeover of the autonomous system. For example, on the autonomous driving cases, when the active safety avoidance systems suddenly take over the driver, it could involve some serious slipping and unexpected the ground situation. So is it a more difficult problem, or is it an easier problem compared to your current work?
Sorry, let me clarify. You're asking specifically the case in which like an autonomous guardian system intervenes when a human is driving the vehicle?
Yeah.
Okay. Yeah, so I think that's it's quite an interesting use case, and certainly one we're interested in. I think, in principle, the model should apply because you always have vehicle dynamics data coming in, and you can always be running your sensing. So effectively, you can be running inference on the diffusion model as this is happening. So there should be no potential need to effectively warm start this algorithm while somebody else is controlling the vehicle. So both the MPC and the diffusion model can effectively be warm started. So you should be ready to take over in that instance.
Oh, thank you.
Yeah, thanks for the great talk. I have a question regarding the frequency at which you run the diffusion model. I think it was 2 Hertz in your slide. Is that because of the inference speed? So is it not possible to run it faster, or is 2 Hertz sufficient? Because I would assume that, especially when driving at the limits, the parameters can also change faster than at 2 Hertz.
Yeah, so I think as a technical question, it is in fact possible to run it slightly faster. We found that this was adequate for control scenarios that we were looking at. More generally speaking, I think you have two timescales on which your vehicle dynamics changes. So there can be more subtle things like thermal effects in the tires as they heat up, particularly when drifting. And these, 2 Hertz is more than fast enough to characterize something like that. The other thing is a very sudden environmental change, like hitting a surface with much lower friction coefficient. Here, I think 2 Hertz is probably about as slow as you want to go, but the robustness of the model predictive control and the feedback you're controlling, the feedback control that offers kind of buys you the time to adapt the model.
Okay, thank you. Let's find the speaker again.
Fantastic. Next up, we have Hang Zhao presenting Uncertainty-Aware Decision Transformer for Stochastic Driving Environments.
Hi, everyone. I'm Hang Zhao from Tsinghua University. I'm presenting our paper, Uncertainty-Aware Decision Transformer for Stochastic Driving Environments. The authors include Zenan Li, Fan Nie, Qiao Sun, Fang Da, and myself. Let's start by introducing the concept of decision transformers. Decision transformers adapt the transformer architecture to reinforcement learning by treating offline RL as a sequence modeling problem. They predict actions by conditioning on historical sequences and target returns. This approach excels in long-term credit assignment due to the self-attention's ability to attribute credit across long sequences. However, decision transformers can be overly optimistic, assuming that conditioning goals can always be achieved despite environmental uncertainties. Let's consider a driving scenario where our ego yellow car interacts with another blue car whose behavior is unpredictable. We divide this scenario into 2 tasks. The first task is going straight. It has a small return variance due to minimum environmental influence. The second task, turning right, is influenced by the blue car's unpredictable behavior, which shows a larger return variance. When considering both tasks together, the cumulative rewards exhibit high stochasticity, making the task very challenging for the ego car to choose an appropriate action. By focusing on only the truncated return from the first task, we can mitigate the future uncertainties. We then summarize 2 properties of driving environments. Let's first take a look at the figure on the left. We train 2 networks to predict return over 1,000 steps and 100 steps respectively, and then normalize the predicted return to between 0 and 1. The return distribution over future 1,000 steps are obviously more uncertain than those over future 100 steps. This validates our first proposition, uncertainty accumulation. The impact of environmental stochasticity on the return distribution accumulates while considering more time steps. Next, we analyze the rollout return versus the distance by selecting the top sequences from our datasets that maximize the future returns over different steps. We find that the returns and distances are closely related. This observation supports the temporal locality property. Driving can be divided into smaller independent tasks where we only need to focus on the current tasks without considering those much later. Hence, optimizing the returns over a sufficiently long horizon optimizes global return optimization. Based on these properties, we propose uncertainty-aware decision transformer, or UNREST. It quantifies the impact of environmental uncertainty, and then learns to drive either aggressively or cautiously depending on the level of environmental uncertainty. We first perform uncertainty estimation. We propose to model the impact of transitions on the return through their conditional mutual information, specifically the divergence between the return distributions P of RT given tau and P of RT given tau and ST. To estimate the return distributions, first, state and action embeddings are processed by two models for return prediction. Then these outputs are fed into the variance networks to predict Gaussian distributions of returns implemented as ensembles, Gaussian mixer models. Then we could compute the environmental uncertainty at time step t using the divergence between these two return distributions. The environmental uncertainty represents incremental information brought by ST for predicting the return RT. The more uncertain the transition from the history to the next state, the greater the informational increment by adding ST is. The visualization below shows our uncertainty estimation results. The left case shows a crossing scenario. As the Eagle car approaches the crossing, the unpredictable light state causes the uncertainty value to rise quickly. For the example on the right, we observe an initial increase in uncertainty as the Eagle vehicle enters the lane and follows another vehicle, owing to the lack of knowledge about the other vehicle's future behavior. This figure shows the architecture of decision transformers. Compared to it, our uncertainty-aware decision transformer first segment the sequences into certain and uncertain parts, and then learn to perform aggressively or cautiously within them respectively. For segmentation, we first estimate uncertainties UT and define an uncertainty threshold epsilon. Then we segment the sequences into certain parts and uncertain parts. After segmentation, the conditioning return is modified. We then define HT as the return span. In uncertain parts, the return span is set to 0 to ignore uncertain return information. In certain parts, the return span is set to the number of time steps from the current to the next segmentation step. During inference, to differentiate between certain and uncertain states, we use a simple KD tree as the uncertainty prediction model. For uncertain transitions, we set the conditioning target to a dummy token. For certain transitions, the planner acts aggressively to attain high returns. Our experiments on Carla shows that UNREST achieves highest driving score and significantly improves safety, efficiency, and effectively increase the success rate of driving tasks. The results indicate that the truncated returns successfully mitigate the impacts of stochasticity. We visualize two typical driving scenarios, lane changing and the red light crossing. Trajectory transformers are overly aggressive, often resulting in collisions, while SPLT is overly cautious and may stand still in many scenarios. In contrast, UNREST strikes a balance between aggressiveness and cautiousness, successfully completing both tasks. For completeness, we have also evaluated our method on D4RL Mujoco tasks. In customized stochastic environments, UNREST achieves the highest reward with lightweight models. Thanks for your attention, and questions are welcome.
Thank you for the great talk. Questions? I can start us off really quick. So, yeah, thank you for the great talk. Yeah, I'm curious. So in the driving settings, can you comment a little bit about how your technique works when you are interacting with drivers that are out of distribution from the data set that you trained your method on?
Yes, based on our method, we will segment basically the long driving sequence into certain and uncertain parts. And we have an uncertainty predictor trying to tell us if this is a challenging scenario, out of distribution, or uncertain scenario. Basically, it will try to, in uncertain parts, it will try to behave more like traditional imitation learning, like behavior cloning methods. And in certain scenarios, it will behave more like offline RL methods. Yeah, so it tries to strike a balance between when I should imitate and when I should behave more aggressively. Yeah, so for out-of-distribution scenarios, I think, we'll behave more closely to the behavior cloning methods.
Is that desirable? Why would I want to imitate something if I'm in a new scenario?
Yeah, we haven't considered much out of distribution, but we are considering more uncertain scenarios. Yeah, I think out of distribution scenarios are something to consider in future works.
Any other questions?
Yeah, just wondering if you can comment on the quality of your uncertainty prediction, particularly in capturing details of the distribution and quantile losses.
In our experiments on CoRL, it performs pretty reasonably. But I think in practical scenarios, in real-world data, I think the uncertainty predictor is something that we should put a lot of efforts on in developing them. And this is also left as future work.
All right, let's thank the speaker one more time.
All right, our next talk will be from Zichen Zhang on polyformer.
Hi everyone, this is Zichen Charles Zhang from Allen Institute for AI. Today I'm very glad to talk about our paper, Polyformer, Scaling Unpolicing RL with Transformer Results in Masterful Navigators. So we start with the question, how to build a masterful navigator? And for object navigation tasks, imitation learning-based policy may use either collect data from the simulation or the real world and scale up the policy model as transformers or diffusion models. Even though they show the promising real-world abilities, it may still have the concern about the out-of-distribution compounding error and limited diversity for the environment and the interactions. And on the other hand, by training in large-scale simulators like AI2 Thor or Habitat, we can enjoy the benefits of unpolicy RL, but the instability and the training speed and the sim-to-real gap may be the bottleneck of the scaling the RL pipeline. And now we introduce the policy transformer. We also call it the polyformer, which is an end-to-end transformer-based policy trained using RL at scale in the simulation. And we formulate our task setting at the object navigation tasks, which means the robot is required to find an object in the environment with specified object categories, using egocentric RGB-only observations. We scale up the both vision and state encoder and action decoder for the architecture. The robot roll out in distributed RL training and large-scale interactive scenes with diverse 3D assets. And as a result, Polyformer achieves state-of-the-art results in multiple simulation benchmarks. And most importantly, it can perform super well in the real world without any adaptations and fine-tuning across multiple different embodiments. And let's first see how the polyformer can do. Here are two policies that are deployed in the unseen real world. And the local bot is tasked to find an apple. It can also deal with a dynamic obstacle robustly. And on the right, the stretchable bot is to find sofa, toilet, houseplant, and book all at once. And now I will introduce our recipe for the polyformer. As I briefly mentioned before, we develop an encoder-decoder transformer-based policy that uses a powerful vision foundation model DynoV2, incorporates a transformer state encoder for improved state summarization, and employ a transformer decoder for explicit temporal memory modeling. And we leverage hundreds of parallel rollouts and large batch sizes, which leads to high training throughput and allows us to train using a huge number of environment interactions. And we use 150,000 procedurally generated Proctor houses with around 40,000 objects from observers. And with this large-scale training, we could get this validation curve showing that the agent is continually improving over training steps and interactions, even over 700 million steps. And now I will discuss about our architecture with more details. So for the input, we use DynoV2 to encode the RGB observation and T5 transformer encoder to encode our Go. And optionally, we also introduce the box nav agent, which uses the bounding box as the specification of the Go if the object had been detected in the current frame. And the bounding box is from the off-the-shelf open vocabulary object detectors. And then the transformer state encoder summarizes the state features, and the causal transformer decoder processes it across time to a state belief, and the user actor critic has to predict action probability and value estimation. And to enable the efficient online RL using causal transformer, we use the KV cache for the past experiences, and use them to only compute the episodic attention scores for the new step. And this reduces the complexity for self-attention from n squared to linear n. And there are definitely some other options for the catching. And here we compare it with the no catch, so basically the traditional frame stacking, and other different places of the model. And here the training FPS. Apparently, the closer to the causal transformer decoder, the more efficient training speed is, and a huge gain than only stacking RGB frames without catching. And now let's see the quantitative results. So in simulation, we first test our local bot in 3 unseen test sets. And 2 years ago, Neuro's best paper Proctor achieved a reasonably good test result in those benchmarks. And last year, the performance was improved by using SingGraph, and earlier this year, embodied codebook further increased the success rate. But seems those increases every year is not that significant. And now we have Polyformer, a huge boost to the previous SOTA in the object navigation benchmarks. And for the stretch robot, we tested on the CoRL benchmark, a recent object navigation benchmark with much more diversity of the houses and the objects. And the previous imitation learning SOTA, Spock, achieved 57% success rate in this benchmark. And given the same training budget for the imitation learning, the previous RL methods could only got 36.5 success rate. And with our training recipe, we observe an almost 50% absolute increase for the RL baseline and 28.5 increase for the imitation learning method. Now let's talk about the real-world deployment. And note again, our policy were fully trained in the simulation, so the real-world environments are totally unseen. And in real-world evaluations, Polyformer also outperformed the baselines by a large margin, and it even outperformed the phone-to-proc, where it trained a policy in testing scenes reconstructed by the phone scan. Next is the result by the box nav agent. So recall that the agent now is equipped with the perfect object perceptions with off-the-shelf object detectors. As we can see, Polyformer has already performed on par with the Spock with the bounding box. And with the perfect perception, our object nav agents can achieve 95.5% success rate in the test unseen houses. It's quite promising. Then we group the test set into 3 difficulty levels to see the failure cases. And compared to the agent without the object perception, the gap here in the easy mode should be resulting from the recognition issue. And for the gap here, for the regular object nav, it could be resulting from the exploration issue, given the same bounding box detection. And for the trajectory in complex houses, the gap became wider because of both the recognition and exploration issues. Now it's my favorite part. So at the beginning, I set our task setting in the object nav navigation, but how about other kinds of downstream navigation tasks? And yes, all of this can be unified by our Polyformer box nav agent by leveraging the off-the-shelf OpenVocab object detector or vision language models like GPT-4V. A single agent can be prompted to perform all tasks without any fine-tuning or adaptations at all. And now let's see how a masterful navigator can do in the real world. So it can follow a remote control car, a person, and can do multi-object navigation, room navigation, and open vocabulary object navigation. And here's the cool results of instance description navigation. The task is to find a book titled Humans. While keeping exploration, we ask the GPT-4V every 10 steps if there's a book titled Human in the image. If yes, the robot automatically calls down. And we also put a few distractor books with other titles, and the agents successfully ignore those and keep exploring the house. We are open sourcing everything, including the model, the training codes, and checkpoints. Feel free to check out our paper and website. And my collaborators and I will be at poster session 4 today from 4 p.m. to 5:30. Thank you so much.
Any questions?
Hey, very nice talk. I'm curious about how this implicit paradigm can memorize long-term searching trajectories. Like, for example, in a large scene, how can the agent to avoid exploring somewhere that it has already explored? Thank you.
Yeah, so actually we use the explicit memory just directly from the causal transformer. And by those experiments, we saw that like when we scale up the architecture, it could actually memory super well. So
okay, thank you.
Yeah, we didn't use any implicit memory modules for those. Yeah.
Okay, thank you.
Any more questions? So how large is the memory? Like, I saw you use frame stackings there. Is that modeling the memory, or like how? Yeah.
Yeah. So for the vision encoders and those encoders that they are frozen, so the entire model architecture would only result in a few million parameters.
No, I mean how many time steps you can memorize?
Is like 128.
Okay.
At the beginning, yeah.
Yeah, nice talk. I'm wondering, have you compared to the recent work like GOAT, G-O-A-T? How I see the methodology is quite different. Like one is learning-based and the other is more like more hand-engineer. How does it compare? Yeah.
Yeah, so we didn't compare it with this work. So this work, basically, we want to develop a kind of more like end-to-end like methods to directly perform the tasks. And for those modular works, I think they definitely have some promising results, but it may have some concern about like in their inference speed. It may have lot of different modules so it may have like different compounding errors. So it's kind of different directions, but we hope that like one single model could just perform well on those navigation tasks.
Okay, thank you.
All right, let's find the speaker again.
Next up, we have Noriaki Hirosa presenting Selfie.
Thank you for your introduction. I'm Noriaki from UC Berkeley and Toyota Motor North America. Today, I'd like to talk about Selfie, autonomous self-improvement with RL for vision-based navigation around people. This work is from collaboration with Drew Fisher, Kyle Stakovich, Ajay Slider, and Sergey Levin from UC Berkeley. Coexisting society with robot is coming in our future. In this society, I think the robot need to behave naturally to be comfortable for all pedestrians and not disturb them, as well as achieving their own goal task. To do so, we can collect data set by ourselves or download the data set and train the policy. And we can deploy it on the real robot. However, in the vision-based navigation, robots sometimes collide with the static obstacle or penetrate in the personal space, which is uncomfortable for the pedestrian. To address this issue, we can fine-tune the control policy on the real robot. However, data aggregation such as Dagger needs expert supervision. This is not scalable. And we have offline to online RL, which can naturally improve the performance autonomously. But the online RL phase sometimes has the performance degradation of the pre-trained control policy and cause unsafe situations. So today, I'd like to propose Selfie, autonomous self-improvement approach, which naturally improves the pre-trained control policy by incorporating model-based learning objective into the Q-value by model-free RL. Our selfie enables us to fine-tune the pre-trained control policy by model-based learning. Model-based learning estimates the reward and trains the control policy by maximizing sum of the estimated reward. However, model-based learning is sometimes insufficient due to inaccurate modeling and limited horizon. Model-free RL can fine-tune the control policy from the robotic experiences in the real world, and generally can consider the longer horizon. However, model-free RL is sample inefficient and unsafe. Our selfie incorporates the orange objective from model-based learning with green objective from model-free RL. In our formulation, so Q bar can be a sum of the residual reward, which the model-based learning cannot consider. Since the initial Q bar can be designed as a very small value, we can stabilize the online learning process. Because the selfie can start the fine-tuning process with same objective as the offline model-based learning. And well-trained Q bar can help really improve the performance and achieve the target robotic behavior. In our evaluation, we apply selfie for the pre-trained Saxon policy for vision-based navigation. However, pre-trained Saxon policy frees in front of the pedestrian and failed navigation. And due to the inaccurate modeling of the geometry, robots sometimes collide with small and transparent obstacles such as glass wall, and robot gets stuck on the uneven floor surfaces. To address these issues, we apply selfie. Before applying the selfie, we pre-train the Saxon policy on offline data set. We train whole network by maximizing some of the estimated reward from dynamic forward model. Then we apply selfie. In selfie, we fine-tune the control policy by maximizing the combined objective. So model-based objective, J-Saxon, and learned Q-value, Q-bar, from learned cryptic. To avoid undesirable robotic behavior, we design following reward function, considering personal space violation, collision avoidance, and not traveling on the uneven floor surfaces, as well as arriving at the goal position. In the visualization, we show the performance of selfie as well as the baseline. For the baseline, we fine-tune the Saxon policy without Q-bar to highlight the advantage of cooperating with the model-free RL. This is a video of selfie. Pedestrian and robot is successfully pass each other, and after that, the robot can go to the goal position. Because now we are penalizing the personal space violation by giving the negative reward. This is a baseline video. Unfortunately, robot gets stuck in front of the pedestrian, and after that, robot tries to find the path to go to the goal, but failed to navigate in this case. This is a more challenging case with multiple pedestrians. The robot can nicely give way to all pedestrians and can go to the goal position. This is the baseline. Robot gets stuck in front and behind the robot and cannot give way to the pedestrian. So in this case, the robot cannot change the path, so the pedestrian is getting stuck behind the robot. To evaluate our selfie performance in human-occupied space, we recruited 12 human subjects and asked them to walk around the robot without explaining which control policy is running on our robot. After each experiment, we asked them 9 questions with 7-point Likert scale. And now, as showing our method, blue bar shows the explicit advantage against 2 strongest baselines. This is another video of selfie with small obstacle. Since we are using the bumper sensor on the robot to detect the collision and give the negative reward, our fine-tuned control policy nicely avoids the collision against the small obstacle. This is another example. As you can see, our fine-tuned control policy shows a nice generalization performance for the unseen obstacle in the training process. This is the last video of selfie for the uneven floor surfaces. Since we are using the acceleration sensor on the robot to detect the traveling on the uneven floor surfaces and give the negative reward, our fine-tuned control policy nicely avoids the uneven floor mat. Thank you for your attention. So more detail is shown on our website, and hope to see you in our poster session.
Questions from the audience?
Thank you for the interesting presentation. I had a quick question. When it navigates through a crowded area with other pedestrians, don't different pedestrians react differently to the robot? Does it have a specific prediction policy for that as well?
Sorry, I couldn't understand the exact your question, so can you say it again?
Yeah, I can clarify again. So do different pedestrians, don't they react differently when the robot is coming in front of them? So would the robot be aware of that when it's planning the actions?
So, sorry, still I'm not so sure what your question, but in my training, we need to estimate the pedestrian's position, but on the inference, we don't need to estimate the pedestrian's position and just running the control policy, and we are feeding only raw observation and goal image view to generate the action command.
I see. The point was that, like, maybe I might walk away from the robot when I see it coming towards me. Somebody else might continue going straight or something of that sort. That was a question I was asking in that sense.
Sorry.
Maybe we can take it in the break, but thank you.
Yeah, let's talk on the poster session.
Certainly, thanks.
Yeah.
Time for one more. I'll ask a quick question. For some of these avoidance maneuvers that you showed, like going around the uneven surface, if I run something like an open vocabulary object detector, I can detect that there's this floor mat, and then I just steer around it with some classical techniques. Where do you think the benefits of certain kinds of factorized or non-factorized paradigms comes into play?
Yeah, I think now we are just penalizing the distance between robot and pedestrian to be comfortable for the pedestrian. But we are not so sure what is the appropriate distance between robot and the pedestrian. I think it's also depending on the robot weight and robot size. So I think the human being feedback or some more nice, so for example, VLM may help to understand more comfortable robotic behavior to train.
All right, let's thank the speaker one more time.
All right, we will have our next talk from Ria Doshi on scaling cross-embodiment learning.
Cool, thank you for the introduction. Hi everyone, I'm Ria Doshi. I'm a fourth-year undergrad at UC Berkeley, and today I'm going to talk a little bit about our recent work, Cross-Former. So one goal that the robotics community has strived to achieve is creating this elusive generalist robot policy, which can be deployed across embodiments and across environments. But usually the way we train these policies is by training on a very limited single embodiment data set, using very limited scenes and very limited sets of environments. And oftentimes we have to tune these policies very well for this one specific embodiment. And so what happens is when the dynamics of our robot changes, maybe a motor starts to wear down, we have to recollect this data and retune our policy all over again. So in reality, these policies aren't actually very general. But what if we trained on data across embodiments? Think bimanual manipulators, navigation robots, quadrupeds. We'd have access to a much broader set of environments, a much wider set of tasks that we could train on, and potentially develop a policy that's more general. In addition, we'd only have to have one single policy, right? Less of this embodiment-specific tuning that can get frustrating to do when dynamics of our robots change. So that's really the promise of cross-embodiment learning, right? Just like we've seen with large language models, perhaps training on more diverse data gets us better generalization and better generalist policies. And so with Crossformer, what we try to see is how can we create an architecture that can successfully train on this cross-embodiment data? Because as it turns out, training on cross-embodiment data can get kind of difficult. For example, different robots have different observation spaces. Your navigation robot might just take in a single egocentric view of the scene, whereas your bimanual policy takes in 3 image views from a workspace view and then 2 wrist camera views, as well as 12-dimensional proprioception. Of course, different robots also have very different action spaces, right? If you're controlling the low-level motion of a quadruped, you would need to control like 12 dimensions, as well as if you're training a navigation robot, that's 2D waypoints. Now, you also have robots that have different control frequencies, right? 20 hertz for a bimanual policy or higher, as well as a Franka robot that may run at 5 hertz. So these embodiments tend to actually be pretty different in many ways. So we need an architecture that's flexible enough to actually adapt to these varying inputs and outputs and control frequencies. And that's kind of what we try and do in Crossformer. By framing the cross-embodiment learning problem as a sequence-to-sequence learning problem, we can reintroduce flexibility into our model. So how exactly do we do this? As input, Crossformer takes in 5 steps of observation history that we feed into a ResNet. Your task can be specified in one of 2 ways. If you're using a language label, you can feed that through your favorite off-the-shelf text embedder, take that embedding and film it into the output of the ResNet. If you're using a goal image, simply concatenate that goal image with your observation history and feed it into the ResNet as normal. We take the output of the ResNet and we project it down into a sequence of tokens. Now, as you can imagine, for a single sample, you might not just have a single camera view or a single input, right? For example, if you're training a single arm embodiment, you might not only want a primary view of the scene, but also a wrist camera view. So you'll tokenize that wrist camera image in the exact same way, and we'll pad all of the tokenizers that we're not using. After we've assembled this input sequence, we append a set of readout tokens at the end of the sequence. We have a set of readout tokens corresponding to every class of embodiments. So for example, all single-arm manipulators share the same 70 end effector action space, end effector delta action space, and so they're assigned the same set of readout tokens. We then compute the attention embeddings for these readout tokens and project them to an action head, or feed them into an action head. And this action head projects that attention embedding down into the dimension of the action that we're outputting on our robot. In this case, 70 end effector deltas, but also 2D waypoints for navigation robots, etc. Each one has its own head. Now, one design decision I want to emphasize that we made here is trying to maximize the amount of parameter sharing that we do across embodiments. Most of the parameters of our model are in our transformer backbone, and our action heads are actually just a simple production layer, so not many parameters in there at all. And we try and share image tokenizers across different camera views that are similar for embodiments. So all manipulator domains have the same kind of workspace image tokenizer shared. We use a training dataset mixture that's heavily inspired from prior work. We use 900K trajectories with a mix from OXC, GNM for navigation, as well as bimanual data and quadrupedal data that we collected. So how does Crossformer stack up in comparison to some baselines? We find that Crossformer is able to outperform or match state-of-the-art performance on 6 very, very different embodiments, from navigators to bimanual manipulators, single-arm embodiments, and more. So when looking at some of the rollouts from this policy, one thing I want to emphasize here is that all of the robots in these videos are controlled by the exact same checkpoint of the exact same policy. So there's no, like, this checkpoint works really well for navigation, so let's use that, and this one for manipulation, let's use that. It's all exactly the same. And we also see some of these nice generalization benefits you can get by training on cross-embodiment data, right? Like, a majority of our evaluations for navigation are done in environments that are completely unseen during training. And we're also able to zero-shot the drone. We treat it like a 2D navigator in that we abstract away the z-axis. But our policy has never seen aerial navigation data before, and we're still able to control it to do quite complex corner-turning tasks. We also compare to the best prior cross-embodiment work, which does action alignment for egocentric manipulation and navigation. A couple things to note here are the fact that this method isn't actually applicable, although it's really good for egocentric manipulation and navigation, it can't actually scale to more embodiments than that, right? You can't use this approach for bimanual, quadrupedal locomotion, or third-person single-arm manipulation. And we find that this action alignment actually hinders performance on some more complex tasks. For example, some of the navigation tasks shown above, but also third-person manipulation, single-arm manipulation. So some takeaways. Crossformer is the first policy to match state-of-the-art performance on 6 very diverse embodiments.
Hello, ladies and gentlemen. We have some packages arrived, but we're not sure who have booked them. Would you mind to come to the front desk to check that out to the postman? Thanks a lot.
Okay, cool. We also use a flexible transformer-based policy to get around the fact that we're using different embodiments. And yeah, all of this is towards building a generalist robot policy. Before we end, I want to give a huge shout out to my amazing collaborators, Homer, who co-led this project with me and has been an incredible mentor, as well as Oyer, Sideep, and Sergey, all from whom I have learned so much, and I'm very grateful. So yeah, feel free to check out our code, model weights. We've open sourced everything, and our website for more cool robot videos. And you can catch me at our poster session later this afternoon. Thank you so much.
Fantastic talk. Any questions?
Hello, thanks for the talk. I was wondering, how did you guys collect your data? Is from the other projects, or did you collect your own data?
Yeah, that's a great question. So a majority of our data comes from the OpenX embodiment collaboration for single-arm manipulation. So not a lot of that data was actually collected at Berkeley. Same for GNM, which is the data set that we use primarily for navigation. For our bimanual policy, we have data collected in Berkeley as well as in other institutions as well, and we do collect our own quadrupedal locomotion data.
So, brilliant talk. It seems that you guys use transformer backbones, and it seems it's not like a decoder-only transformer. But right now, so most popular transformer are decoder-based transformer. Do you guys think it's necessary to use pre-trained transformer, such as LM, or you can just bootstrap a transformer? Is it which one do you think is better?
That's a great question. So right now we train our transformer entirely from scratch, but I do think that a lot of recent work has kind of explored using this like vision language backbone to enable better generalization to new objects and such. I definitely think there's a lot of power in that line of work, and so definitely a cool area to explore in the future.
You mentioned something about a motor degrading and it working, right? What happens there? Your inputs would still be the same as if the motor were working. How would it recognize it?
Yeah, so that's a good point. Here, I guess the point that I was trying to make is that when we're co-training a policy on a lot more data, we might require less new data to be collected on this degraded motor robot than we would if we were entirely training this policy from scratch on bad data.
Do you think this framework can be generalized directly to a reinforcement learning setup in which like different tasks will have different reward?
That's a good question as well. I'm not sure. Right now, we train our policy entirely from demonstrations, so we do imitation learning. But I do think that it would be really cool to incorporate learning from suboptimal trajectories somehow, and RL would be a great kind of method to do that. So I think that's a great area for future work.
Okay, let's invite the speaker again. Okay, I think that's the end of session. Thank you.
Do you want to? It's 12 o'clock, I think.
Great work, great work. Yes.
All right, now we have a small break, so we'll see you guys back here for our next oral sessions at 11 o'clock. Please enjoy the break and the posters. Thank you.